Hello and welcome to Organic Chemistry. I'm Mr. Collard. In this tutorial, we're going to finish our discussion of organic reactions by specifically looking at an overview of polymerization, addition polymerization, condensation polymerization, esterification, combustion, saponification, and finally fermentation. Let's examine polymerization. Polymers are organic compounds made up of chains of smaller units covalently bonded together. Polymerization is the process by which individual units called monomers are linked together to form larger chain structures known as polymers. If we examine the word polymer, the prefix poly means many and mer is a member or a unit of some larger structure. Polymers can be synthetic or natural. Examples of synthetic polymers include nylon, rayon, polyethylene, and polyurethane. Naturally occurring polymers include proteins, starches, and cellulose. Polymerization can occur in two ways: addition polymerization and condensation polymerization. Let's examine addition polymerization. All monomers are added together in addition polymerization. This type of polymerization almost always involves the opening of a double or triple bond. Thus, unsaturated organic compounds are needed as a reactant. Now here's an example of an addition polymerization, and the key thing to be able to do here is just merely recognize this as addition polymerization. You have a monomer, you have an unsaturated hydrocarbon, and we have the opening or breaking of one of the two, in this case, bonds of the double bond, creating an unpaired electron to form a new single bond linking the two reactant monomers to make a longer chain polymer. Let's examine condensation polymerization, otherwise known as dehydration synthesis. Individual units are linked together by removing a water molecule. Two products are formed, the polymer and a water molecule. Condensation polymerization requires that there be two functional groups on each monomer. Let's look at an example. The formation of a polypeptide by joining two or more amino acids by condensation polymerization reaction, otherwise known as dehydration synthesis. You may recall this word being used during the living environment course. Here's amino acid number 1, here's amino acid number 2, and we're keying in on the OH of the organic acid group here from amino acid number 1 and the hydrogen atom of the amine group of amino acid number 2 to form the peptide linkage, otherwise known as an amide bond. Esterification is another example of condensation polymerization. Let's examine esterification. Esterification involves the reaction of an organic acid with an alcohol to form an ester and water. Esters are associated with smells. Sometimes they're pleasant, like flowers and perfume, and some esters have a not so pleasant smell to them. The general format of esterification involves an alcohol reacting with an organic acid to produce an ester and water. It's worthwhile to commit this general format of an esterification reaction to memory. One thing to note is that the ester product contains carbon atoms. The water product does not. Thus, the ester product is known as an organic product, and the water is known as an inorganic product. That is to say, inorganic being not containing carbon atoms. Let's look at an example of esterification. Methanol and ethanoic acid combine to produce methyl ethanoate and water. Water is an inorganic, non-carbon containing product. Methyl ethanoate you'll recognize as an ester because you can see the functional group here. And from the name, methyl, first name ends in YL, last name ends in the OATE ending. And if you go to table R and you search through the examples and you match up the name methyl ethanoate and look at the endings with what's on table R, you can recognize this structure as an ester. Here's methanol, one carbon alcohol with its OH functional group here. Ethanoic acid is a 2-carbon organic acid with the carboxyl or organic acid functional group here. And in the green dashed box, we can see how the alcohol and the acid are joined together by pulling out the water molecule. Let's examine combustion. Combustion is the most common type of organic reaction. Almost all organic substances will burn. Sufficient oxygen is needed so that carbon will burn to produce water and carbon dioxide. When water and carbon dioxide are the only products of a combustion reaction, we call that a complete combustion. Refer to Table I of the chemistry reference tables to see a list of combustion reactions. The first 6 listed on Table I are organic compounds burning in air, and we know air is a mixture of gases. The gas in air we focus in on for combustion is oxygen gas. Here we have our first 6 reactions on Table I, and we recognize the organic reactants here and oxygen gas as reactants to produce carbon dioxide and water in each case, and this column involves energy. The unit of kilojoules you can find on Table D, selected units, and the J stands for joule, which is a unit of energy, and kilo means 1,000. Let's examine the combustion of propane. Propane we recognize as a saturated hydrocarbon, particularly an alkane, recognizing the ane ending, and the prefix prop, meaning 3 carbons, C3H8, reacting with oxygen gas in a complete combustion to produce carbon dioxide gas and water, and an energy term here, 2,219.2 kilojoules. Since this energy term is on the right side or product side of the arrow, this means that energy is released to the surroundings. Here's this reaction on Table I. At this point in the course, we're not going to examine in detail what delta H means, why this is a negative sign. We just want to recognize, even from real life, that propane is a common fuel used in propane gas grills, and that is a reaction that you're probably familiar with to cook food. The burning of propane in oxygen gas will release energy to the surroundings, which could be absorbed by your hamburger or steak or your grilled vegetables on your grill. Let's examine saponification. Saponification is the hydrolysis of fats by bases to produce soap, and the word saponification has the word soap in it with the first 4 letters if you rearrange them. The general format of saponification involves an ester reacting with a base to produce alcohol and an organic compound called soap. Example would be the use of fat combining with a strong base to produce glycerol and soap, and that is shown in this diagram here. Now, you're not expected to be able to draw out this diagram, nor are you expected to memorize this by any means. You're simply asked in this course to be able to recognize the organic reaction saponification involves the production of soap, and to be aware of the general format of the reaction. Finally, let's examine fermentation, the process by which enzymes from living organisms act as catalysts in the partial breakdown of organic compounds. Alcoholic fermentation is a chemical process in which yeast cells secrete the enzyme zymase and break down sugars into alcohol and carbon dioxide. The general format for this type of fermentation involves sugar reacting with an enzyme to produce alcohol and carbon dioxide. Here's an example of glucose, C6H12O6, and if you recall from living environment, word that ends in OSE means sugar. The enzyme breaks down this organic reactant to produce a 2-carbon alcohol called ethanol and carbon dioxide gas. What did we learn in this tutorial? We gained an overview of polymerization. We examined addition polymerization, condensation polymerization, esterification, combustion, saponification, and finally fermentation. Need more help? Please contact me. Have a great day.